Morning, everyone. So yesterday we started looking at some practical aspects of a titration. We've done a couple titrations. Essentially, the goal of a titration is to find some unknown concentration. We drop in one solution via a burette, basically using the solution in the burette called the titrant to count how much unknown particles there are. We divide up by how much we pipetted into the Erlenmeyer on the bottom, and we can calculate the initial concentration. I showed you a slightly different setup of doing a titration. This advantage is we don't need to worry about, oh, now the phenolphthalein has turned to pink and now I need to start over. In this case here, by actually using a pH probe and sampling the pH as I actually drop in the titrant, I can actually plot a curve. I can still find the equivalence point here, and I can still find the unknown concentration this way. So we're just going to have a look at some of those main curves here. I wouldn't memorize any of these curves here. But see if you can just sort of rationalize it out here. We've been so far been doing, oh, I have my acid in the bottom solution. I've been dropping base in. What if I switched everything around here? Let's see if we can still work out our logic. So let's just start off here looking at our curves again. I want you to just consider with me a strong acid, strong base curve. It can still very well just be, let's do HCl and NaOH, right? Our typical strong acid, strong base. I know it's going to neutralize to form table salt, and it's going to end up forming water. And what I'm going to do this time is I'm going to flip it around just to test your logic here. This time what I'm going to have is some unknown amount molarity of NaOH. I don't know the concentration of the base. And what I'm going to do is I'm going to drop in acid instead, right? It didn't matter which one was where. In this case here, my acid, I would know the concentration, but let's just say this is HCl for now. And effectively what's happening here is we're starting off at the beginning with a ton of hydroxide, and slowly over time we're going to drop in the H plus to count how much hydroxide there is. Again, you can totally do this using phenolphthalein with an indicator, no problem. I just want to do this again with a titration curve sort of setup. So for a titration curve, in our lab here, maybe actually be a little bit tedious because we don't have a drop counter or whatnot. But essentially what's going to happen is you're going to stick a pH probe inside, and it's going to constantly sample the pH as you steadily drop in the acid. So our titration curve here, relatively, it plots pH on the vertical axis. It plots volume. This time what I'm dropping in is acid, so volume of acid added. So that's going to be different from previously we've done volume of base added. Well, my pH probe at first, when I have dropped in 0 acid, so I haven't dropped in anything yet, my pH here of the base should be fairly high. So if I have 7 as my dividing line, remember 7 is neutral only for 25 degrees. Because this one here is a strong base, we would imagine that the curve would start out very, very high, start out at a very high pH, because this one here is very, very basic. What's going to happen to this as I steadily drop in acid? Well, as I drop in acid here, the H plus slowly kills off the hydroxide. Dropping in acid should lower the pH. When I'm at the really sort of high end of the pH here, strong bases would typically knock me into the maybe pH 12 to pH 14 sort of range. Weak acids at regular everyday concentrations may only be like pH 8, pH 10 or so. So we start out really high, but as you drop in acid, we're going to expect this line here to start coming downwards. Part of it, again, is due to that logarithmic scale here. When I get so far away from 7, I'm actually losing quite a lot of base particle. It's just not super obvious on a logarithmic scale. There will be a very special point, however. So it keeps dropping, keeps dropping, keeps dropping, and then suddenly it's going to shoot downwards, probably even steeper than that. Shoots downward like this. And we had said, well, that occurs. I may have the last remaining drop of hydroxide. It's still a basic pH. I drop in an H plus to kill it off. That's when I hit equivalence point. I'm going to remind you some of this terminology here. Equivalence point is perfectly when your moles of H plus has matched up to moles of base. I've counted perfectly how much acid solution there is. I went from that single last drop of hydroxide. I've killed off all the particles at equivalence. At equivalence, it's always going to be the middle of this jumping down region here. Equivalence point, if you remember from yesterday's class, because this is a strong acid, strong base, nobody wins. There's actually no salt that hydrolyzes, so the pH is going to be exactly 7 at equivalence point. And then as I start dropping in H pluses, they really can't find any extra hydroxides to cancel out, so they're going to just not only be acidic, but they're going to steadily become more and more acidic as I slowly drop in H plus. Okay? So that is my titration curve here. Why does it look different from the one from yesterday? Well, yesterday we were looking at volume of base added. We were looking at the curve actually going upwards. This time we're dropping an acid, so it has to come down this way. So let me, again, rehash for you some of the vocabulary here. We talked about the equivalence point here as this middle of this jumping region. The volume that's needed for this time I'm adding acid, so I'm going to say VA. This is going to be called the volume of acid needed for equivalence. And I just want to make this note here. You notice that within a very, very narrow volume, within a single drop or even a half drop here, the pH suddenly changes. Right? It blows right through this point here. So even if we're going to use phenolphthalein for an indicator, phenolphthalein changes color between 8.2 and 10. That's actually a little bit early, in this case here for equivalence point, but pretty much by the time you run through when the indicator changes color, this time it's going to be pink to colorless. I'm pretty much going to run through the equivalence point as well. So normally if this was a typical titration, we'd just go straight to our equation. Well, we have HCl, it's reacting with NaOH. This is supposed to be becoming NaCl and water. Let's verify that at equivalence point y is pH 7. At equivalence point, the HCl and NaOH are perfectly cancelled out. That's when the moles I've added perfectly follows the mole ratio. The NaCl is a table salt. It potentially could hydrolyze. NaCl becomes Na plus and Cl minus. Well, Na plus is a group 1 ion, spectator. Cl minus is a conjugate of a strong acid. Because both of them are spectators, no extra hydrolysis, no extra reaction with water, so therefore the pH is actually 7, as we would expect. At equivalence point here, the acid should have killed off the base. In a typical titration then, we may have an unknown amount, like molarity of NaOH. I would have pipetted in a certain volume, maybe 10 milliliters. I would be able to track the volume from the burette, take 2 readings starting and ending. That would be the titration volume. I would know that, and the whole point of a titration is we're going to use something that I know the concentration to find the unknown concentration. We did a few practice questions over the last day here. Basically, you're going to take the thing that you know more, find moles, you're going to mole ratio over, and you can find the remaining amount. Okay. So even if you did this graph here, you can just read, well, this is the volume that I needed for the color change to occur. That's when I stop. That's actually going to be this volume where I actually stop. Okay. Careful, your formula does sometimes end up looking like C1, V1, C2, V2, but be really careful. Sometimes the mole ratio is not 1-to-1. If it were like the example from yesterday, we did sulfuric acid, it was actually a 2-to-1 ratio. If you just accidentally did it as C1, V1, C2, V2, you'd be missing that part there. Okay. All right, so that's a titration curve here. That's pretty much all we can do for a strong acid, strong base curve. What I'm going to do now is I'm going to ask you to consider, take this curve and imagine just swapping it out on me. Imagine instead of this being a strong acid, strong base curve, let's throw in acetic acid. So acetic acid in the presence of NaOH. We studied this a little bit with our buffer systems. We're going to see it on a graph this time. This one here, again, neutralization occurs. Acetic acid, although it's not really good at ionizing, it's still the H plus that's going to react with OH minus. We're going to end up getting sodium acetate, so that's already one difference. And we're going to end up getting water, fine. We started off with just pure acetic acid. So let me see if I can just line up this graph here. So the top graph here is a strong acid, strong base curve. And what I'm going to do on this bottom curve here is I'm going to plot what would it look like if it were actually a weak acid instead. Let me actually pull it over a little bit so hopefully it's a little less confusing. So this one here is for my acetic acid equation. So all I've swapped in on you is I've swapped in a weak acid, strong base curve. Now, if you just memorize from last day, okay, well, the strong base wins. It's going to knock the equivalence point here up into the pH above 7 region. That is totally correct. But let's just sort of get back to that. So, looking at the acid and the two acids here, HCl was a strong acid. It was a one-way arrow. It formed H plus and Cl minus. Acetic acid is a little bit different, though. Acetic acid as a weak acid, its Ka is a lot tinier. Reactants are favored. Although it too is able to donate an H+, it's not as good. So probably what will make this a little bit clearer here is, imagine I have a box full of HCl. Imagine I have 1 mole HCl. Back when things were just strong and it was just one-way arrow, this one would 100% give all the H+. It's that H+ that ends up dropping in to cancel out the hydroxide. Well, what about acetic acid though? Acetic acid, I also may be, let's say, 1 molar, I may be a box fill, but because the Ka constant is so tiny, I actually don't have a lot of H plus actually used to react. This may give you the misconception that, okay, well, if weak acids here, let's write in words, the weak acid produces less H plus due to low ionization. It doesn't dissociate, it doesn't break off that easy. So even though I have my base solution in here, instead of dropping in HCl, which guarantees me it's going to get a ton of H+, I'm going to drop in acetic acid. It's a little bit sluggish, and it's basically, oh, the acetic acid here doesn't really generate a lot of H+. It would then say, okay, well, if I don't have that much H+, if I compared equal concentrations, let's say both of these were 1 molar for argument's sake, maybe that would imply, yeah, of course, by the end of it, if you add enough acid, this side here would still be volume of acid added. Maybe if I add in enough acid, well, since there's not as much H+, maybe I need much more volume to actually hit equivalence point. Strangely but surely, though, if I actually compare them, if these were really equimolar, if they're the same molarity, yes, I'm going to get a few interesting parts. I'm going to get pH versus volume of acid. I'm not going to be up into the 12 and, oh, actually here, in this case, I still will be up into the 12 and 14 because that depends on the NaOH. So I'm going to still start out fairly high. But what's going to happen here is we're actually going to end up having a very interesting buffer region, right? There's going to be a sort of buffering curve. There's a part that the pH doesn't look like it's changing. And where this sort of jumping down region occurs here, it jumps down at exactly the same volume that it took for the strong acid to do. As you keep adding acid, it's going to definitely steady out here. So there's two questions for us here. First question is, how come that it was the same volume that was needed to reach equivalence point? And the second question refers to how come there was a buffer that was formed. Okay, we're totally right. A strong acid here ionizes 100%. HCl are not holding hands anymore. As I drop in HCl, they 100% become just pure H+, and they kill off OH-. When the equivalence point is reached, moles of H+ has killed off moles of OH-. Similarly, it's true, the weak acid here does not ionize very well. You're going to drop in acetic acid. As you drop it in, it's not going to have that much H+. But here's the kicker. When you actually drop in H+, who is H+ going to react with? Well, the little amount of H+ I drop in is going to find an OH-. The H+, finding an OH- gets neutralized, it ends up forming water. What is that going to do to this equilibrium reaction? Well, for starters, the Ka wasn't very big. I don't actually generate a lot of H+. But as that H+ gets neutralized, it ends up actually shifting the equilibrium over. So we're actually not depending on the weak acid being able to ionize all at once. It actually ionizes very little, maybe 4%, maybe 3% or so. But let me just write this down in words. As this titration occurs, as titrant is added, the NaOH neutralizes the H+, shifting the equilibrium to the right. Now there's sort of two reactions that we're sort of involved with. This is sort of the big equation. This is the acid-base neutralization. That's not an equilibrium. But what we know is the hydroxide is going to slowly kill off the H+. Well, since the weak acid was actually in equilibrium, as we kill off H+, it's going to pull the acetic acid over. So even though we're totally right, acetic acid doesn't ionize very well to begin with, because I am steadily killing off the H+, I keep replenishing it. I kill off more H+, I replenish it. I'm going to basically eventually get rid of the same amount of H+. If they were equimolar to begin with, I basically use this neutralization to actually pull the equilibrium over. I'm not relying on just the natural dissociation in helping me form the H+. So, as the titration is added, NaOH neutralizes shifting equilibrium right, and this actually explains it's the same volume to reach equivalence. Doesn't matter strong or weak. The only difference is a strong thing. Right from the get-go, it would actually break up. There's no H holding hands with Cl. I have maximum amount of H+. The acetic acid takes a little longer, so it produces just a little bit of H+. You neutralize a little bit of it, it produces more, until the acetic acid is gone. Once there's no more acid, that's when your equivalence point is reached. Alright, so that's one problem. The equivalence point here is still going to be when I have this sudden jump. And in this expression here, we notice that when we have, in this question, it was a weak acid strong base curve. we had said the pH, the base wins, the pH is actually slightly bigger than 7 at equivalence. Why is that? Right? If it was strong acid, strong base, it's exactly 7. Well, that really comes down to the salt. At equivalence point, the acid has killed off the base. Right? I've perfectly cancelled out H plus and OH minus. What about this Na CH3COO though? The Na plus, still a spectator. That's just going to swim around in solution, not do anything. What about the CH3COO? The CH3COO is actually going to hydrolyze. This one here is actually a conjugate base. This one can actually reform a little bit of acetic acid and reform a little bit of OH minus. I am at equivalence. At equivalence, it means I have no more reactants present, but because my product, the salt, ended up forming, the salt is able to hydrolyze because we end up getting anionic hydrolysis. We end up generating extra hydroxides. Yes, we do actually make some acetic acid as well, but again, if this one were still relied on to actually produce H+, we get even less of that. So just even though we're at equivalence, we produce extra hydroxide, and therefore the pH is actually slightly bigger than 7 if so if I put X for my sort of equivalence point here, maybe that red marker here would have been where pH 7 is. Doesn't have to be by much, but the equivalence point is slightly higher. So in terms of choosing an indicator, something like phenolphthalein would be perfect. Phenolphthalein is known to change color between 8.2 and 10. That's exactly the region I want. You can be really silly and choose an indicator, maybe as a Ka value where it changes color at pH 3. You can do the reaction. You can watch the color change. But if the color change is not occurring where I want it to occur, where I want it to tell me, oh, the reaction is over, then that's actually going to do you no good. So this is a link to tomorrow's lesson here. We will want to choose an indicator like phenolphthalein. Choose an indicator with an endpoint. Endpoint is also sometimes called a transition point. Careful, those two terms are different from equivalence point and stoichiometric point. Stoichiometric point had to do with, well, as the name suggests, the stoichiometry, the mole ratios. The endpoint has to do with the indicator. The endpoint is when the color change happens. So I can choose a silly indicator where, oh, the color changed, but that told me nothing about the equation. I want to choose an indicator whose endpoint, when it changes color, it's roughly around the equivalence point. That's roughly when I know I want to stop the titration. Okay, so that's one interesting note about a weak acid, strong base curve. The other question that I had was, how come earlier we didn't have any buffer region? It just steadily dropped and then steadily dropped here. This part here is more so due to the logarithmic nature of the scale. As I get really far away, it gets harder and harder to gain in the y-axis. But notably here, if one of them is weak, we have a definite buffer region. Let's just remind ourselves here, what is a buffer? Right? A buffer is a solution that has good amounts of conjugate acid and conjugate base. It maintains the pH. It tries to keep the pH from jumping too high, from decreasing too low. Right? This buffer here is able to moderate the pH. In this case here, we definitely have a weak acid. So definitely we have CH3COH. We're definitely set up so that it's unsurprised that we have a buffer. Right? We have an equilibrium. That's why we need to shift left, shift right. For starters, we just had acetic acid. Right? So little of it actually ionized over. We get a little bit of H+, a little bit of acetate. For a buffer, remember, it has to be able to moderate pH changes for both acid and base. It has to be able to shift left and shift right. Now, one way of making a buffer we had said before was, oh, let's just add in a salt. Let's just artificially beat this up. You didn't see me add the salt. All that's happening here is we had our acetic acid in the burette, and I'm steadily dropping into the base. This one here is that second, more complicated way of making a buffer. Let me just add some numbers to this here. Initially, the example I gave you previously was, let's say I have 10 molar of your acetic acid. Initial is before anything has happened, so 0 and 0. What I'm doing in this situation here is I'm actually adding base. I'm actually slowly killing off the acetic acid. So we now have a little bit more familiarity. At equivalence, I would have needed to add, if it's 10 molar, I would need to add 10 molar NaOH to kill off all the acetic acid. What if, instead of adding, so at equivalence would have been plus 10 molar of NaOH. But what if I was only halfway to equivalence? That's going to be exactly halfway of what the VA is. That's going to be labeled as V half later on. So halfway is going to be 5. So I would have added in 5. The acetic acid and NaOH react in 1:1 ratio. I would have killed off 5 of the acetic acid. I would have gained 5 of the acetate. At that point, I would actually, at the half equivalence, I would still have a good amount of the conjugate acid and a good amount of the conjugate base. And whenever I had appreciable amounts of both of those, I knew I was a buffer system. I did not artificially come up and create this acetate. It's just based on the neutralization. I haven't quite killed off all the acid yet, but I have been steadily forming acetate. If I draw pictures to this here, I've definitely no longer 10 molar. I've lost a lot of it, but I now still have good amounts of both the conjugate acid and conjugate base. So at V half, it actually puts us smack in the middle of the buffer region, so that for a little extent, if you start adding in some more acid, I'm going to still want to neutralize it here. If you add H+, oh good, I have enough acetate, I can shift to the left. If you then add some base here to try to go back up the curve here, the base is going to kill off the H+, it's going to go downwards, great, I have enough acetic acid, I can shift to the left. So I formed this buffer without actually needing to add the conjugate myself. So let's write this down in words here. So this buffer here, at V half, the NaOH has neutralized half the CH3, COH, into acetate with appreciable amounts of both conjugates. The solution can buffer the pH. And again, when you say, okay, what's the buffer's job? Is to minimize really big changes. The pH is still going to change. If you really track, the pH is never going to be constant there, but it's definitely not going to decrease as quickly or increase as quickly as without a buffer. We had talked about buffers having a capacity. Basically, there's a limit. What if I use up all the acetic acid? I wanted to shift right, but I couldn't anymore. So in that situation, the buffer would run out, and therefore it's going to shoot down one way or shoot up the other way. And that's called the buffer capacity. That actually more so refers to the actual starting molarities. If I had a buffer that was like 5 molar, I'd have a good buffering capacity, a good range to actually buffer in. If I were, let's say, 0.5 molar and 0.5 molar, I'm still a buffer. I'm still going to be exactly at this pH, but I don't have a lot, and I'm going to run out a lot quicker. So this shooting up and shooting down is going to happen a lot earlier. So that there in general is just referred to as a buffering capacity. We've made a buffer by neutralizing half, and it doesn't have to exactly be half, but the sort of best buffer is when I have equal amounts of the acid and the base. Okay, so that explains a couple key features with this curve here. We're going to go through this curve in a little more detail here with a little bit of math. And I'm just going to flip it around again just to make sure we can't memorize anything, so we have to just sort of analyze the situation. Okay. So let's take another look at this weak acid strong base curve. So I want you to consider we have an unknown weak acid reacted with a unknown strong base. Okay. This time, like yesterday, I'm going to flip it around, right, just to test your logic here. I'm going to say this is our strong base. Let's say it's NaOH. Right? It could be anything hydroxide. I'm going to drop in an unknown acid. For an unknown acid, it may even say an unknown monoprotic acid. All they're trying to emphasize here is, as an acid, you should have an H. Monoprotic means you just have one H. If I was diprotic, I'm H2A, so on and so forth. Even though my goal of this titration is to find the unknown concentration, what I'm going to do, in running it through a titration, basically there's going to be some unknown amount of H+ in here. If it's really, really concentrated, you're going to run through tons and tons of titrant. Remember, we only have a 50 ml burette. Usually I tell people fill it up something more than half, right? And that way I don't have to reload in between. Every time you reload, you're going to introduce some air. That's why we do a rough titration to begin with. Let's make sure these molarities here are very similar so that I'm not wasting through tons and tons of solution. Let's plot out what is our titration curve going to look like this time. So pH, always on the vertical axis. This time I'm back to volume of base added, so be it. I'm going to stick my pH probe in here. This time I actually don't know a lot about the acid. I don't know the concentration, and I don't know the identity. I can't just look up the Ka constant. So we're going to need to do a titration curve to actually figure out the unknown here. Are we going to start out, let's put our 7 here, are we going to start out at a pH high or low? Well, I'm sticking my pH probe here into an acid solution. I'm expecting it to be low. I don't necessarily know if this is strong or weak. Well, actually, they told me it's weak acid, so I don't know the concentration, so I don't know for sure, but I would expect weak things to be somewhere maybe pH 6 to pH 4. Strong acids would be down to the 0 to 2 sort of range, right? Rough, just numbers here. So because this is weak, I would expect it actually starts out somewhere higher, right? I'm going to call that pH initial. That's going to become an important point later on. The starting point of pH is actually steadily, it's a little bit high. I haven't added in any base yet. What's going to happen to the pH as you steadily add more and more base? Okay, so add in a little bit of base. I expect the pH to go up. It's going to go up. Add a little more base. It's going to go up. Add a little more base. It's going to go up. Because we are dealing with something that's weak, this weak acid, let me just write out a generic equation here. I'm going to get H plus and A minus. Just like the acetic acid we had just talked about, I start off with some unknown amount of HA. A really, really tiny fraction goes to become H plus and A minus. As you steadily start killing off this HA, there's sort of two equations that I'm considering at a time. HA is steadily being killed off by the NaOH. There is overall going to be a neutralization. We're going to end up getting NaA, and we're going to end up getting water, right? There is a point called equivalence point when the NaOH has killed off the HA. As I reach the half equivalence point, just like earlier, I would have converted some of the HA into the A minus form. So I would naturally have formed a buffer system here. Because of that equilibrium, because I'm able to shift, I would expect here there would be some leveling off region sort of early on. Okay. As I sort of go beyond that buffering capacity, as I really do run out of HA, I go from having that last little drop of H plus, last drop of acid. Now I have no more drops of H plus, so now I'm going to be at equivalence point, and then I drop in an extra drop of base. It's going to switch from acid to base in a very, very narrow range of pH. So this is going to suddenly shoot upwards. As you keep adding base from there, here it's just going to keep going up this way. If you compare this graph to what we did earlier, hey, there's a lot of familiarities, right? In this case here, oh, it started to drop down because I was adding acid. Well, there still was a buffer region. There's still this shooting up point here, and the equivalence point was something bigger than 7. Notice I've indicated that for you here. There was a natural buffer region, right? This was created at the half equivalence point. The equivalence point, the point when the stoichiometric numbers are correct, the stoichiometric point here, equivalence point, I'm going to call this time VB. This is the volume to reach equivalence. And within a very, very narrow band of volume, within maybe a half drop, I've gone from an acidic pH through equivalence into a basic pH. Okay, the equivalence point is always going to be sort of midway here. We had already talked about, well, the equivalence point is actually, the pH is actually higher than 7. Let's just write that down again here. At equivalence, moles of H plus is equal to moles of OH minus. So I have no reactants left over, but it's actually this NaA. It's going to dissociate to form Na plus and A minus. The A minus, I don't know what it is just yet, but being a conjugate of a weak acid, conjugate of something in equilibrium, this A minus can actually anionic hydrolysis, reform HA, and end up forming OH minus. So it's going to add extra base. That's why even at equivalence, we're actually a little bit higher than 7. That's a very favorite question of theirs, so make sure you know that one. At equivalence point here, the reactants are gone, sure, but it's actually the salt. If it doesn't hydrolyze, perfectly pH 7. If it hydrolyzes, if it's the anion, it's going to be on the basic side. All right. What I'm going to do here is I'm going to do a little bit more math with this. So I have VB. We talked about there's a special point here at V half. I've converted half of my HA over to A minus. I'm going to take VB, whatever this number, and I'm going to take exactly half of it. Half of it, I'm going to call it V half. And that's going to put me smack in the middle of my buffer region. Right? That's the point when I have equal amounts of conjugate acid, conjugate base. We're going to read the pH at that point, and we're going to call that pH half. So there's two pHs that I'm interested in. One was the initial pH. The other pH here is going to be called pH half. Okay. Now this is sort of as bad as this question gets. I don't know the concentration, nor I don't know the identity of it. Okay. So let's start working on it. First one that I'm going to need to do, I will eventually need an ice table. Ice tables need the equilibrium constant expression. So I need to figure out what the Ka is. So what we're going to do, we're going to look at the V half point. So we have HA in equilibrium with H plus and A minus. Let's start off with some initial concentration. The Ka for this is H plus times A minus over HA. We just said at V half. At V half, you've converted half of your HA over to A minus, so therefore, HA is actually equal to the A minus. That's smack in the middle of your buffer region, and what that allows us to do is HA cancels out A minus, perfect. If you want to find the Ka, you just need to find the H plus at this point. Well, I have a bunch of pHs. pH is the negative log of the H plus. I can actually take negative logs of both sides. pKa is actually the pH half. Okay, so let's write down in words here. Since at V half, the amounts of conjugates equal, we end up with this relationship here. The A minus is equal to the HA, so pKa is equal to pH half. So if I did this graphically here, if they actually plotted it out for me, I can just read VB here is when it shoots up. I'm going to take half of that. I'm going to find what the pH is at this coordinate here, what's the y-axis, and that is actually going to give me pH half, and therefore I can undo it. Ka is the anti-log of negative pH half. So even with an unknown acid, I can actually figure out the constant. That's the first part. Second part here is, well, the whole point of a titration is to find the unknown concentration. For the unknown concentration, I now am interested in the initial amount. Well, naturally here, before the acid was present, the pH was supposed to be 7. It was only after the ionization of the acid that the pH has actually dropped to pH initial. So this is actually the second step here. We've looked at the importance of pH half. We can actually derive this expression Ka is equal to 10 to the negative pH half. Now what we're going to do is we're going to focus on pH initial. So let's pretend here we started off with just pure water. Water here is supposed to just have pH 7. The only reason why the pH actually started dropping lower was because you started adding this unknown acid, HA. And what we're going to do is we're actually going to set up an ice table. HA is in equilibrium with H plus and I minus. Our ice table, just like we did in our Ka calculations, we have an unknown starting concentration. I'm going to say concentration of I. We're going to pretend that the initial, this part here is before any dissociation, any breaking up. Before breaking up, I had no H plus, I had no, A minus. Right. So I have none of the ions there. As I shift towards equilibrium, this side's going to minus x, this side plus x, plus x. We're going to get concentration initial minus x. We're going to get an x and an x. That's the reason why our initial solution, when you stuck your pH probe inside, why there is a pH initial anyways. From pH initial, you can just read it from the graph. What does your graph say? Your starting pH is maybe 3 point something right now. My pH initial, you can read from the graph. Well, pH initial is the negative log of the H plus. Yes, I would say initial, but in terms of this ice table, well, the H plus had to have come from the acid. So this is actually the equilibrium amount of H plus. So what we can do is we can actually find what is the H plus on the equilibrium row. It's actually just put the negative over, anti-log negative pH initial. And therefore, we have our final expression. I know I just did this with a lot of variables here. Let's just find, well, what's Ka? The equilibrium expression for this ice table, it would be the H plus times the A minus all over the HA. The H plus and the A minus, they are both identical to anti-log of negative pH initial. So 10 to the negative pH initial, whatever that number is from your graph, you square that number, so pH initial. On the other side here, we're going to divide it by your starting concentration minus x. X was, again, 10 minus the pH initial. Right? And we had actually calculated Ka. Ka was actually anti-log of pH half. So there's two special points that you need to identify on your titration curve. That halfway point, that initial point, I can do a little bit of rearranging here just to clean it up a bit. The concentration initial minus 10 to the, I'm just pulling that to the left-hand side, pH initial is equal to this 10 to the minus pH initial. That one there is squared, pH initial. I'm actually going to divide out the purple term, so 10 anti-log pH half, and all I'm going to do is I'm going to add that term over. This gives us a final expression. We'll do this as a virtual lab so you can actually play around with this. So therefore, our final expression, sorry, my writing is getting really messy here. We have 10 to the minus pH initial, 10 to the minus pH initial, divided by 10 to the minus pH half. Those are all coordinates I can find on the curve, and I can add it to 10 to the minus pH initial. Okay. And at the end of the day, with the titration curve, I didn't need to use an indicator. I have been able to find my unknown concentration with this expression. I need to know the pH initial, just read that from the y-axis. I need to know the pH half, and that's it. All right. So I'll leave it off there. We'll practice through a virtual lab so you can see this worked out, and then we'll go from there. Thanks, guys.